Okay, so good afternoon to everyone. And yes, so I'm going to, in this school, there are 3 lectures related to the atomic clocks in particular, even though Professor Fritz really gave touched a little bit on that thing, but he was mostly on systematics and statistical errors and etc. And he was taking clock as an example, but there are 3 dedicated talks on clocks. So one is mine, and 2 others will be given by Professor Tanya Melstromner from PTB. And so we have divided in such a way that I will sort of give an introduction to the atomic clocks, and I will discuss about the microwave atomic clocks. And Tanya will describe more on the optical atomic clocks and related applications and etc. So today I will, the introduction of the atomic clock, I will give basics, which are related, which needs to understand the atomic clock and describe the microwave atomic clock. Okay, so let's begin. So let us understand what is clock. Okay, if we talk about clock, the first thing comes in our mind is the pendulum, right? That's the simple thing we know. Atomic clock comes much later. So what it has, a pendulum just oscillates, it has some time periods, and using that property, one can measure time. And here the time is not the absolute time starting from like Big Bang, but it's a time difference. When we call it time, it's actually a time difference from now to maybe 1 hour later or something like that. So if you have an oscillator, or let's say pendulum, and if you know what is the oscillation time period, let's say 1 second, and if you count number of oscillations, if you multiply these 2 things, then you can practically find out what is the time difference. That's the basic principle of any clock, irrespective of atomic clock or any clock. So practically you need an oscillator and you need a counter to count these things. For example, let's see if you have a pendulum which has an oscillation period of 1 second, and if you count 60 of them, that means you are counting 1 minute, 60 seconds. Okay, like that. Okay. So let's see, like, what should be the property to make a clock? What are the 3 things? So this is again the same pendulum. It has, let me just briefly tell you how this thing works mechanically. This is a mechanical pendulum clock, right? So this pendulum oscillates and it's connected to a wheel. This wheel has multiple teeth. So these are like individual teeth. And this pendulum and wheel, they are connected by a anchor and fulcrum. What happens due to each oscillations, this wheel rotates in such a way that it just goes by 1 teeth. And this fulcrum basically counts that how many teeth are going, 1, 2, 3, 4. So in every oscillation, this 1 teeth will move, and this, using this fulcrum property, one can count how many teeth are moving after n number of oscillations. So to make a very good clock, what you need a stable oscillator. So the oscillator's time period has to be really like whatever it is. Let's say 1 second, it has to be really 1 second. So there should not be any damping and etc. If you measure it today, if you measure just after a second, or if you measure after 1 year, this should have the stable oscillation time period. And the second thing is the least count of this entire thing, which is basically this teeth. So that would give you what precision you can measure. Like you can measure it 1 second accuracy, or half a millisecond accuracy, or 1 minute accuracy, whatever. That's the least count of this teeth, how the teeth has been built. The third thing is you have to have a very reliable counter. This, let's say you have a wheel where these teeth spacing are not exactly equal, then you will miss the like number of counts and etc. So you need a very reliable counter so that you do not want to miss any count. So these are the 3 important things. If you somehow make them proper, then you can make a very accurate clock. So which are these 3 things? Accurate, stable, and precise. So stability of the oscillator, precision, precision, like at what precision can you measure? If you remember the talk by Fritz Resel, he was really giving the definitions of each of them. And what sort of accuracy you can achieve. And finally, once you have all these things, the last part is really just display, and you can have a very fancy display to display the time what you read. Like for example, there is a clock, it has a display, but the inside of the clock is something like that. It has some oscillators. Okay. So again, coming back to the same thing, so I described three things: accuracy, stability, and precision. It was again described by phrase, but let me just go through once again. Let's say if you have an archer and there is some like targets, it's divided into different zones. The red is most accurate zone, and you are like throwing, let's say 10 arrows. So what could be the situations you can end up? You can end up to this kind of situation. So your all arrows goes to the exactly center and everything is proper. It could be situation like that. It could be situation like this. It could be situation like this. Okay. Now out of all these four different combinations, which one is accurate? Which one is precise? Okay. So let me just show you which one it is. So for example here, so this blue line is the true value. What is true value, you understand, right? Like what is the actual expected value, not the what is the mean average of the measured value. So this blue one is the true value. And in this case, you see your all data points are nearly across this true value. In this case, this is the scenario is something like that. There it is like this, and there it is like that. So there, this one is the true value, and your average value is somewhere above or lower compared to the true value. Now, out of this one is a very accurate, stable, and precise measure, right? Wherever this one is not accurate, but stable and precise measurement. So in any experiments, even the best experiment in the world, can you tell me that which situation you will end up to? You will, even if it is a very precise, accurate, like no, not accurate, even if it is a very like sophisticated measurements, you will end up to this situation. You will never be able to measure exactly the true value. There will be always some bias, always some shifts, and that is systematics. So then what you have to do, you have to find out what is this shift practically due to the systematics like black body radiation. You remember Fries was telling about a list of all these possible systematic shifts like black body radiation, Zeeman shift, second order Doppler shift, blah, 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 etc. So you will end up to this situation, and then you have to estimate how much is it shifted from the true value, and you have to encounter that part into your measured thing, and you have to say, okay, this is how far I am from the true value. So any measurements, any based measurement, you will always end up to that. You can also end up to this one, but hardly, I mean, it's nearly impossible to end up to this situation. Okay, I hope I am able to tell you what is the difference between precision, accuracy, and stability. This is the three very important things for any precision measurements or like, let's say, yeah, accurate measurements. Okay, so now coming back to the clock in general. So in this plot, what you see in the x-axis, this is almost like 700 years. And this axis is saying, if let's say a clock is running over some certain time period, then over which time period the clock will give you 1 second inaccuracy. So that is telling like this time period over which the clock will sort of give 1 second inaccuracy. And to help you a little bit, I just put little markers here, like this is corresponding to 1 minute. This is something like ice age. This is like age of our earth, and this is age of our universe. So you see, like let's say, let's just, I mean, you see like this early mechanical clocks, something like 700 years ago, this was 1 second inaccurate over just 1 minute time scale. But that's, we don't need to go that far. Let's just go about 120 years, which is sort of the time scale that we have the quantum mechanics, or we know which the quantum mechanics started. You see, over 120 years, we have improved enormously in this clock thing. Yeah, so like 120 years is somewhere, let's say, here. So there, this was like even before cesium beam clocks or something like that. So it was accurate to, no, am I right? This is, yeah. Something like 1 second inaccuracy over 2.6 million years. Whereas today we have reached somewhere here where the clock is 1 second inaccurate over 300 billion years. It's much more than the age of our universe. Physically, that is a meaningless thing because there was no clock before the age of the universe, but assume that there was a clock 300 billion years ago. And if it is running until today, it will just give 1 second inaccuracy. And why that clock is needed, etc., that I hope Tanya will describe more. I will not cover it into this lecture, but that's really needed for fundamental science experiments and etc., etc. So we have reached to this level until today. Okay, so this now coming back to the atomic clock, to the beginning of the atomic clock, the first concept was given by Professor Rabi, and he got Nobel Prize in 1944, and that just year after, and you remember that is the era of Second World War. So precision timings or time synchronizations was realized very, very important because all these radar, etc., weapons and all these things were coming, the more advanced versions of that, and it was realized that precision timing system is a very important thing. So 1945, just 1 year after his Nobel Prize, he gave the idea that actually atoms can be the best oscillator. He got Nobel Prize for NMR and all these things. So he said that atoms can be the best and most accurate oscillator. And why that is the case? Because the oscillation frequency of an atom, what do I mean by that? Let's say two-level system, ground state and excited state. For example, this one, the oscillation frequency of electron between these two things, these two energy levels, that is much, much higher compared to a standard pendulum. So electron can oscillate 10 to the power 10 times or 10 to the power 15 times, depending on you are looking into a magnetic transitions or an electric dipole or electric quadrupole transitions, whatever it is, but the oscillation frequency is extremely higher compared to a standard pendulum. And why that is helpful? Any idea? Let's say you have a pendulum which is oscillating 1 per second, and in this case, if your counter, see, none of the counters can be perfect. There is always something, some error into everything. Yeah, let's say your counter misses just 1 count, that means you are missing 1 second immediately because the oscillation period is 1 second. But if a oscillator has an oscillation frequency of 10 to the power 15 in 1 second, and in this case, if you just miss 1 count, then you are missing a really very small fraction of a second. So that's why it is helpful that if you have a very fast moving or oscillating pendulum, there your chance of making error is much, much smaller. So that's why larger oscillation frequencies always makes a better clock. Then the atoms are the most stable oscillator. You can take an atom anywhere else in the world, or you can, let's say an hydrogen atom, it has the exact same property. It has some systematic dependent shifts, for example, Zeeman shift, etc., but that we know how to estimate. We know for a particular state what would be the systematic shift, or we can know, we can find it out. So considering that we can take care, that kind of systematics we can really, really take care. It's a really unperturbed system, and hydrogen atom everywhere in the world or everywhere in the universe is the same. Whereas, let's say, an artificial atom, for example, a superconducting qubit or an NV center, each of them are different. If you take a quartz crystal, from batch to batch, these quartz crystals are not same. It depends on how it was grown. So they have a different property. So that's the advantage of an atomic system or ionic system, because they are, each atoms and ions are identical, exactly identical. They are not different. And if somebody want to make a clock or something like this experiment, they want to have a system where each system need not to be calibrated. You just make a cesium clock. Every cesium clock will be same by its property. It doesn't have any aging or any change in property. If you take any quartz crystal, due to humidity, due to moisture, or whatever, every property of the crystal will change, but atom doesn't change. I mean, in the beginning of the universe, there was hydrogen atoms. It's the same property today, assuming fundamental constants are same. Okay, it's a most unperturbed system. If you can choose a system which has a very least perturbation in the external fields. What do I mean by that? Let's say the energy states, which let's say these are the two energy states, and we can choose some particular transitions which are associated to some states which are least perturbed, and these perturbations are, for example, black body radiation shift. Like we can choose a state which has a very minimal polarizability or zero polarizability if it's a spherical, like let's say S cell or something like that, or very minimal quadruple moment. So that quadruple shift is very minimal or zero. This kind of things, what I mean by that. Okay, identical in nature, I already said. Now, like with the advancement of this laser cooling trapping or ion trapping techniques, which you have just learned in the previous lecture, we can really trap them, cool them to microkelvin temperatures, and we can keep these atoms and ions in a very, very small volume. And that volume is in very well controlled environment. What do I mean by that? Over a, let's say, 100 micron diameter, a sphere of 100 micron diameter, or even in 1 millimeter diameter, we can sign an electric field or magnetic field with perfectly homogeneous field. Perfectly means nothing can be perfect, but something which is below our level of considerations. So we can practically apply a magnetic field and electric field or whatever we need in a very homogeneous field over that 1 millimeter volume. But if you have a atomic beam over, let's say, 1 meter long atomic beam, I will come to that thing, you cannot maintain that sort of homogeneity. So with this advancement of the tools, which Anders was mentioning, that nowadays this laser cooling and these things becoming practically a tool. There is no research at this moment, but we just use these things as a tool, and using these sophisticated tools, we can really control everything within that small volume and environment. Okay, so due to all these facts, these atomic systems are very, very like pure, neat, and unperturbed systems where atoms can be used as an oscillator. That's the bottom line of the slide. Okay. Now let's understand the basic principle of the atomic clock. It's practically very simple. You consider a two-level system just for simplicity. So atoms to start with are in the ground state. You apply some excitation field. It could be microwave or laser field depending on the transition frequency. And you excite the electron to an excited state, but that electron will not stay forever in that state. It has some certain lifetime, so it will radiatively, it will decay back to the ground state and it will produce a photon that is called fluorescence. Now, if you change the frequency of this exciter across the resonance, then you will sort of get this kind of line shape, which is a Lorentzian line shape. Now, if you measure this line shape, then practically you have two informations here. One is the central frequency corresponding to the maximum of this line shape, which is nu0, and the line width, which is delta nu. So then you can say, roughly speaking, that we are able to measure the central frequency with an accuracy of delta nu. Actually, one can do much better than that, which I will come. But just for now, you can measure the central frequency with the best accuracy of the line width of this transition, which is delta nu. Okay, and once you measure this nu0, if you remember the definition of the time, if you can somehow measure this oscillation frequency, which is in this case nu0, then you can convert it into time. Inverse of the frequency is nothing but time. Okay, so that's the basic principle of the atomic clock. And the atoms have this kind of energy level structures, and we have lasers, we have cooling and all these techniques, etc., which we have to implement to make it much better and so on. Okay. So now this kind of transitions, like you have seen these transitions, can you take any transitions in the atomic level? No, you cannot. So you see that the property is this line width. So if you take a transition which has a very narrow line width, that means you have a better chance to make a more accurate clock. So you have to choose some transitions which has a very narrow line width. And you know, typically what we know that electric dipole transitions, we read the selection rules for the electric dipole transitions in the textbook and etc. But that doesn't mean that the higher order transitions are not allowed. Quantum mechanically, they are allowed. These are like for electrons, this is like electric quadrupole transitions, octupole transitions, and etc., and magnetic dipole transitions, and so on. So if you take an electric dipole transition, the line widths are quite broader. It's like tens of megahertz. Whereas if you take an forbidden transitions, for example, electric quadrupole or electric octupole transition or magnetic dipole transitions, the line widths are very, very narrow, and it could be as narrow as 1 nanohertz. Okay, so instead of 10 megahertz, one can go up to 1 nanohertz, or let's say between friends, it's 1 hertz. Okay, so that means if you choose such transitions which has a very, very narrow line width, or on the other way of saying, a forbidden transitions which are allowed by quantum mechanics, then you have a better chance to measure the center frequency with better accuracy. Okay, for example, let's say a transition frequency nu0 is, let's fix it to 10 to the power 15 hertz, which is an optical transitions, typical optical transitions. And considering nu0 is 10 to the power 15, if you take a electric dipole transitions, which has a line width of 10 megahertz, then this quantity, which is nothing but fractional frequency accuracy, that quantity becomes 10 to the power minus 9. Whereas if you take delta nu, a transition which is only 1 millihertz line width, then this quantity becomes 10 to the power minus 18. So by choosing a very narrow transitions, one can enhance the accuracy. This is a fractional accuracy. One can increase the enhance this fractional accuracy by many, many fold. So the bottom line is you have to choose a forbidden transitions to build an atomic clock. You cannot use an electric dipole transition which is just allowed and which is much, much wider. Okay, and some example of this kind of transitions, again, like these are like electric quadrupole transitions, electric octupole transitions, and if you know the Wigner-Tackert theorem, then by expanding that thing, like you have a different matrix elements, and they also follow different kind of selection rules compared to the electric dipole transitions. And one example is like for ytterbium ion, it has both of these electric quadrupole and octupole transitions. For example, at 435 nanometer, this is an electric quadrupole transition, and it has a 467 nanometer transition, which is an electric octupole transition. And this transition, electric octupole transition, is 3 nanohertz line width. Okay. And there is another kind of forbidden transitions where in, let's say, for example, strontium atomic system, and this is S to P, singlet S to triplet P, but you see this is 0 to 0. That means the angular momentum, what is happening to the photon's angular momentum? It is not conserving. Yeah, so what is happening? Because this triplet P0 state is not a pure triplet P0 state, but due to hyperfine interaction, it has an admixture of all other excited states like that. Okay, and that admixture is allowing, very slightly allowing this transition, and that's why this is an highly forbidden hyperfine induced transition. This is another kind of forbidden transitions. Okay, so we have to choose this kind of transitions to build an atomic clock rather than just electric dipole transitions. For example, this S to P transition is an electric dipole transition which has a line width of 10 megahertz, whereas this one has a line width of 3 nanohertz. Okay, now let's just put all the atomic clocks in one table. So this is like hydrogen measure. This is 1s to 2s transition of the hydrogen based on that. So these are the operating frequency of different atomic clocks. These are the fractional accuracies on the order of magnitude, not exact. And these are the achieved stability, again, order of magnitude. This is the rubidium clock, which operates at 6.8 gigahertz. This is the cesium clock at room temperature, not with laser cooled and anything, which commercially available. So these three clocks are commercially available. You can just pay and buy it. And this is cesium fountain clock that uses the magneto-optically trapped laser cooled cesium atoms, and I will come to that thing in detail. And using that, you can enhance the accuracy. And finally, the optical clock, which has the best accuracy so far in the world. And you see, like, there are several orders of magnitude. So this is, look into this thing. This has reached to below 10 to the power minus 18 level, whereas the hydrogen measure has an accuracy on the order of 10 to the power minus 13. But of course, building these things is many fold complex compared to the hydrogen measure. And that's why these two type of clocks are not yet commercially quite available. Okay, now let's go through little bit of basics, even though many people have covered it, but I will go a little bit faster in this case. So basically you understand that for building a clock, you need to have an atom photon interaction. And this photon could be in microwave, photon could be in the optical domain. And again, this two-level picture, like if you excite the atom, it will have some lifetime in the excited state and it will radiatively decay back. And how many times it can go back and forth between these two states per second is defined by the scattering rate. Anders was exactly telling you these things. So scattering rate is how many photons you can scatter. That depends on few parameters, like where exactly how far is your excitation frequency corresponding to this frequency difference between these two states, which we call detuning. Okay, so that is this factor delta, depends on the line width of the transition, depend on how intense laser are you using, and that compares to the saturation intensity, and that is the S0 is the saturation parameter. It's intensity of your excitation, like let's say laser, divided by the saturation intensity, so that's called saturation parameter. So depending on all these parameters, you can get an effective scattering rate, and this gamma is the maximum allowed scattering rate. But depending on how far are you detuned, what is the intensity and etc., you get an effective scattering rate, which is always below the maximum scattering rate. Okay. Now, the picture what I was showing you in the last slide, that was sort of like the atom is going into the excited state and coming back. But if I look into a time scale shorter than that, or let's say on that time scale, then what will happen? And if we keep our excitation frequency on, a resonant field will excite the atom. The atom or electron basically will go to the excited state. But then if we keep that field on, due to stimulated emission, that atom will again come back, stimulatedly come back to the lower state. If we wait further, then the stimulated emission will not happen, but it will radiatively decay. So that's called fluorescence. But here I'm talking about the stimulated emission. Okay. Now, so let's come back to the block. I mean, I am just building few things before I use these tools. So you understand this like smaller time scale excitation and all these things. And because I am building these things, because I will come back to the Rabi frequency. Now, another thing is block sphere, which was again introduced, but let me just quickly go through you. So let's say, again, two-level systems, ground state and excited state, and these two levels are connected by some excitation frequency, some exciter. Then you can basically create a superposition state. And in this thing, what will happen? So the possibilities are the atom is either in the excited state or in the ground state, but it could be also there is some superposition. So these are two pure state, and the superposition state is something like that, where you have superposition of this ground state and excited state. It will have a like this theta and phase factor, which is phi. Now, if the theta is pi by 2, then you will get this kind of superposition with a phase difference in between. And if you get a pi means this theta is pi, and then you can practically excite the entire, excite the atom entirely to the excited state. That is, so you can tune this parameter in the experiment. You can tune this parameter theta with proper length and etc., which I am coming in my next slide. Then that is called a pi pulse. And if you apply a pi pulse, then entire atom will go from the ground state to the excited state. But in between, there will be a superposition state. Okay. So if you now keep on applying these pulses, you will practically give this kind of oscillations. It's called Rabi oscillations. And if you wait further, if you wait quite a bit, it will sort of come back to a 50% things and 50% chance between ground state and excited state. That means basically, if you now think about an ensemble of atoms, 50% atoms will be in the ground state or 50% atoms will be in the excited state, or other way around, if you think of a single atomic picture, then the atom will have a 50% chance to be in the ground state and 50% chance to be in the excited state. But if you look into the beginning, practically with proper tuning, let me just go into the next one, you can practically transfer all the atoms to the excited state. And that is called, that's duration of the pulse is called pi pulse. And by playing with detunings and intensity, we can tune what fraction of the atoms we want to transfer to the excited state. It could be 50%, it could be even lower or whatever. Now this is a plot. This is the probability of being into the excited state, and this is the omega t. Omega is the Rabi frequency and t is the time. So this is an effective Rabi frequency. Effective Rabi frequency depends on the unperturbed Rabi frequency plus the detuning of your laser or microwave photon, whatever it is. So the maximum omega can be omega 0 if the detuning is 0. Now this t is the interaction time, over what period the atom is interacting with this exciter frequency, let's say laser or microwave. So that would depend on what is the length of that interaction. Let's say this table, and I have an atomic beam which is going in this direction and the laser is coming just against of it. That means my interaction length is length of this table, right? So that is L, and V is velocity of the atom. So the interaction time will be basically L by V. That is how long the atom is staying within this laser field. Well, I'm many times saying laser because but it could be laser or microwave, whatever. So this is these two things, okay? Now, again, I'm just following the same picture. If I put it in mathematical formulation, then this rho, that is the probability of being into the excited state, that depends on these quantities. That is detuning of the laser, velocity of the atoms, length of the interaction zone, and what is the unperturbed Rabi frequency. Okay, I just told you how they are dependent. And analytically, you can just write these things. It's like 1/1 plus delta by omega 0 square times sine square, this quantity interaction time, L by V, square root of omega square plus delta square. So if delta is 0, you can get maximum of it. But the point is, let's say the condition when delta is 0, then this omega 0 t, so if it goes out of the square root, so then omega 0 and this L by V is the quantity t. If I set it in somehow a pi, which is called pi pulse, then practically I will get all the atoms to the excited state, right? That's the definition of the pi pulse. I mean, I have shown you how it happens. Then the probability of being the atom into the excited state becomes exactly 1. But not necessarily it has to be always the pi. So if I plot this quantity rho with respect to this delta over omega 0, so that part, you can also take omega 0 out and then make it delta over omega 0 square. If I make a plot, then I will get the Rabi oscillations like this. This is the Rabi oscillations. So what would be the line width of these oscillations? That is this line width, this delta, which is nothing but omega 0. And is omega 0, if my omega 0 t is equals to pi, if this condition satisfies, then omega 0 becomes pi over t, and t is L by V. So putting that thing, so it's become pi V by L. So line width of my Rabi oscillations will depend on interaction length and velocity of the atoms. Okay, and what do I want to make a precise measurement? I want to have this line width as narrow as possible, right? Then I will have a better chance to measure the center frequency. How do I do that then? So I can either increase L, so I can have a very long interaction zone, or decrease velocity, right? And how do I do that? So L increasing means increasing the interaction length. But the problem is, let's consider an atomic beam and you have some sort of interaction like microwave cavity or laser field, something. Even if you have an atomic beam, it will not be straight always, it will have a projectile motion. So atomic beam will at some point will bend. You cannot infinitely increase the interaction length, right? You can do it up to a certain limit, maybe a meter, maybe 1.5 meter or 2 meter, but it cannot be very, very long. So then better thing to do is like decreasing the velocity, but that's also complex. but it's achievable by laser cooling and doing all these kind of Sisyphus coolings and etc. You can decrease the velocity from 600 meter per second to few centimeter per second. That's what laser cooling does. But that's much more effective. There's several orders of magnitude in gain. Okay. So I hope I'm able to tell you that why laser cooling or how laser cooling actually increases sensitivity of the entire atomic clock things. This is the reason why I brought this Rabi frequency and Rabi oscillations and etc. Okay, so that was like what Rabi spectroscopy, by measuring these Rabi frequencies, doing the spectroscopy that was like formulated by Rabi during 1940s and so on. But you see, the problem is what did he find out at that time? Reducing velocity was not possible because even the lasers were not there. So laser cooling was out of question. So the only possibility was increasing the length. And up to a certain limit that is probably possible, but beyond that, that's not possible. And the disadvantage of this technique, even though that technique works fantastic, that was a really, really marvelous thing what he told us, including many other things. What I was telling you, like keeping the homogeneity of the field over that long interaction zone. Assume that you can do it like 10-meter interaction, but can you create a field which is exactly homogeneous over 10 meters? If it is not, then it will give some other effect. That's not possible. So this is one of the disadvantage. And second thing, what I was telling you, that you cannot increase the length infinitely. Maybe few meters, something like that. Even few meter, even a meter is quite challenging. So then his student, Ramsey, he did a little bit modification of Rabi's technique, and that worked quite fantastic. What he said, that you actually don't need to have a very long interaction zones, but let's use the effect of interference. So you, instead of one big pulse, you put two small pulses and keep the atoms non-interacting in between. Okay, so so in this case, what happens if you shorten this pulse width, then over that very small interaction zone, so atoms are interacting here and here with the microwave field, but they are not interacting in between. They are just freely moving. What happens over these small interaction zones, you can really keep the field extremely homogeneous. So instead of having this big table, you just make it very small, and over that part, you can really keep the microwave field very, very homogeneous. So that was a fantastic thing. And second thing is, yeah, so practically that's it. And that works much better. So I won't go into mathematical derivation of these things, but I will pictorially tell you that how it exactly works. This is practically nothing but interference effects. So I'll pictorially tell you how it works. But before that, is there any question? Then I can answer that, and then, okay, yeah. Sorry, I cannot hear you.
Sir, you told about some scattering rate before the block sphere representation.
Yeah.
So on which parameter does it depend? Like, how can I improve it?
Yeah, so I was telling you the scattering rate depends on the saturation intensity and detuning. So this is the scattering rate. This is the maximum scattering rate which is possible, which is defined by the lifetime of the excited state. You know, gamma, that is the inverse of the lifetime of the excited state. And the effective scattering rate depends on detuning of your microwave or laser field from the actual resonance frequency and how intense is that field. This S0 is called saturation parameter, that is relative intensity compared to the saturation intensity. There is a parameter called saturation intensity, which again depends on Rabi frequency practically. So let's put it in this way: the intensity or strength of that field and detuning of that field. Any other questions? Can you please switch it on? I cannot really hear you.
Actually, that gamma by 2, that factor depends on line width only, right?
Yes.
Okay, yeah.
Yeah. Okay. Now let's try to understand how this interference effect works for the Ramsey spectroscopy. So I have told you already about the Bloch sphere concept, and that's the reason I was actually telling you about the Bloch sphere, because I am going to use it here. So now let's say this is my first interaction zone, and the atoms are interacting with the microwave field over this small interaction period. So what will happen at the end of the interaction? Let's consider the microwave will end exactly at that phase, okay, phi 1. Then the atoms will acquire that phase phi 1, and it will keep it within it. It will keep it within its memory, and then it will freely evolve, but the atom will have that phase phi 1. However, within this free evaluation period, the microwave will propagate, will keep on propagating. In the next time, in the next interaction zone, the microwave will appear at a different phase, let's say phi 2, but the atom keeps in its memory that phase phi 1. So due to this phase difference between atoms and the microwave where it is interacting, this will give you an interference effect. Interference effect is nothing but the phase difference. Okay. So due to the phase difference between atoms and the microwave that is interacting, that gives a interference effect practically. And by the way, if you want to go to the mathematical thing, you can look into these things, this reference. Okay, then what will happen? Let's say this is one of the Rabi oscillations or something like that. It will further split into multiple fringes. That's what interference happens. So instead of like limited by line width of this entire oscillation, you break it into further pieces, and you can actually finely measure this line width of this fringe. So instead of basically having the line widths of maybe hundreds of megahertz, now you are coming down to some hundreds of hertz by this technique. So that was a very, very good improvement and given by the Ramsey, which improved the accuracy of this kind of frequency measurements, and therefore improved the accuracy of the clocks. Okay. And now if you somehow, like let's say these laser cooling techniques, if you somehow decrease the velocity, you can even fine tune these things or finely split these things, then it could be even the line width becomes less than 1 hertz, even in microwave field. So that means you can measure this transition frequency between two ground state and excited state with an accuracy of below 1 hertz. Okay, so let's say if you have the transition frequency of 10 to the power 10 hertz and you are measuring this with an accuracy of 1 hertz, immediately you are getting delta nu by nu 0 10 to the power minus 10. And if you're in previous case, if it was 1 kilohertz, 1000 hertz, then it is 10 to the power minus 7. So it's several orders of magnitude improvement. Okay. Now coming back to the more time related thing. So cesium clock, cesium is our present SI definition of second is based on cesium. And why cesium? Because cesium has a very neat energy level and it has one valence electron in the outer core. It doesn't require any isotope selectivity because it has only one naturally abundant isotope. Rest of them are like they don't exist because of the radiation. Radiative nuclei. It has a very well separated ground state. The ground state is doubly splitted. Like this is the ground state of an unperturbed system. And due to hyperfine interactions, this is splitted into F is equals to 3 and F is equals to 4, which are separated by 9,192,631,770 hertz. Exactly. Okay, so roughly speaking, 9.2 gigahertz. It has two MF is equals to 0 state. That means there is no first order Zeeman shift. Okay, in the magnetic field, they will in first order they will have no shift. So practically, you can select the Zeeman unshifted state or MF is equals to 0 state between F is equals to 3 and F is equals to 4, this transition to make a very accurate clock because they are Zeeman unshifted and all these things. Okay, so the present SI definition of second is the time required for this many number of oscillations between these two states of cesium atom. You remember the time definition is number of oscillations times time period of each oscillation. So SI second is defined at this many number of oscillations, the time required for this many number of oscillations between two hyperfine ground state of cesium atoms. Okay. So there are two kinds of cesium clocks. One is the atomic beam clock, where the cesium atoms are at room temperature around 300 Kelvin, and in the other case where the cesium atoms are at very, very low temperature, almost close to 0 degree Kelvin, that is around 330 to few hundred microkelvins. And these are two sort of pictures, and let me go through these two things. Yeah. So in the cesium beam clock, practically you have to first produce the cesium beams. So this is the two levels of cesium atoms, F is equals to 3 and F is equals to 4. And remember, the one valence electron of cesium, it has an electron spin of obviously 1/2, and the cesium nucleus has a nucleus spin of 7/2. So the 1/2 and 7/2, they can couple, like 1/2 and 7/2, they can be parallel to each other or anti-parallel to each other, right? So due to the relative direction of nuclear spin and electron spin, you can consider them as two different magnets. So where electron spin is parallel to the nuclear spin, and in our other case, the electron spin is opposite to the nuclear spin. So that's what these two little magnets are, two little magnets are showing. So we can imagine them as two different magnets just oriented oppositely in two different states. Okay, so to begin with, if you have an sort of, let's say, oven where the cesium atoms are there, then you will have a 50% admixture, 50-50 admixture. So 50% atoms will be here, 50% atoms will be in this state. And you somehow create an atomic beam. That means this is a storage, a reservoir. You make a small hole in the beginning, in front of it, and you heat it up a little bit. So through that small hole, these magnets will come out, right? But then you use some Stern-Gerlach effect. So that means you use some magnetic field gradient. And what happened in the Stern-Gerlach effect? Two different spin states, just they follow two different paths, right? That's what is happening here. So one magnet will follow in this path, the other magnet will follow some other path. So let's say this F is equals to 4, the atoms which are in F is equals to 4, they follows this path and they go out of your system. So that is basically a state selection. You are selecting a particular type of magnets for your experiment. That is called state selection, and you are doing it by using Stern-Gerlach effect. Then you are taking these atoms into the microwave cavity where you apply microwave. And then if your microwave frequency is proper, which means the microwave frequency is on resonant between these two states, if it is on resonant, then they will excite these atoms from here to F is equals to 4 state, right? So then what will happen if the frequency is right? It will excite the atom to the excited state. Then in the second stage of this deflection magnet, which is Stern-Gerlach again, it will again deflect back. If it is not in the right frequency, they will just go in a different direction. And you keep your detector in such a way that you get a signal as soon as they are excited. As soon as your microwave frequency is exactly correct, they goes into the other state and they will deflect and they will fall on your detector. And then you will get a signal and you put it in the microwave source and lock it. Then you have a reference of this signal, which is corresponding to this 9192631770 Hz. You know that you have excited all the atoms because you have seen the maximum count rate on your detector. So you now calibrate your frequency, and that is your frequency reference, and then you can derive the time reference from it. Okay. So this is how it looks like exactly inside. So this is a glass tube and you have this microwave Ramsey cavity. Okay, by the way, so this is not a single interaction zone. So the microwave interacts at this point and at that point. In between, it is a free moving thing. That's exactly what you see here. So microwave interacts here, and in between, it's a freely moving thing. And this is Ramsey cavity. And this is the first deflecting magnet. This is the cesium oven, this is the second deflecting magnet, and these are the detectors and etc. So as I told you in the beginning, when laser cooling and etc. was not there, people were trying to make bigger and bigger like atomic beam clocks. So atomic beams are very, very long to get better and better accuracy. And this is one example from NRC Canada, which I believe something like this is the microwave interacting cavity. This is something 1 meter, and rest of the parts are detection and all these things. And that is one of the longest cesium beam clock. And today you can actually get everything in a small box, the cesium beam clocks, because practically you cannot do much better by increasing length, because you cannot increase the length more than a meter or something like that. So everything is very compact and commercially available. This is name is 5071A, and this is the size of a computer, this CPU size, and one can get it. And the typical accuracies is fractional accuracies on 10 to the power minus 14 and so on, which is quite good. Okay, so far so good, but can we improve further? And how can we improve further? The only way we can do better job by decreasing the velocity of the atoms. So then the laser cooling thing comes into the picture. And why it is helpful, let me explain. I explained you why decreasing velocity is helpful, but let me explain you in a much simpler way. So you understood that there are two interaction zones, and in between it's freely moving particles. So if I use just a simple uncertainty principle, delta t times delta E is greater than or equals to h bar by 2, where delta t is the flying time in the non-interacting zone, and delta E is the frequency uncertainty. So delta E I can write in terms of h times Planck's constant times delta f. So and then delta t goes here. Then practically I can derive delta f by f0. I am just dividing it by f0, then 1 over f0 times delta t. So you see, this is fractional frequency uncertainty. And fractional frequency uncertainty is inversely proportional to delta t. That is this freely moving time, right? And how can I increase this freely moving time? By laser cooling. Okay, so this gray line is the Maxwell's Boltzmann distribution for any atomic beam, let's say. And if you do laser cooling, then you can actually create lot of atoms at this lower velocity class. You perturbed this Maxwell-Boltzmann distribution, and you shift some of the hot atoms at higher velocity to lower velocity. Okay, and then you use these low velocity atoms in this atomic clock thing, and then you have this delta t enormously manyfold larger compared to an atom which is, let's say, 600 meter per second velocity class and etc. And that's how you improve. So then you improve, like you get down from several hundreds of hertz to like 1 hertz or even less than 1 hertz line width. Okay. Okay, so this is like laser cooling, which was already explained, so skipping. So how this fountain then works, this is the cesium energy level diagram. So the laser, which is typically used at 852 nanometer, and this is a magneto-optical trap, which was explained in the previous lecture, so I'm not going into that. This is the cesium atomic beam, which, okay, let me just go back. So, so first, using the magneto-optical trap, you collect some millions or billions number of cesium atoms. It's an ensemble of cesium cloud, which are very, very cold to 30 microkelvin or so. Then you give a little bit kick of these atomic balls upwards. Okay, and then these atoms go upward, and there is a microwave cavity in between. So while going upward, they interact with this microwave cavity. They reach to a certain height, and from that height, they again fall back. And they fall back through the same cavity. Okay, due to the gravity, they fall back. So they fall back to the same cavity. So then you have two interactions through the exact same cavity. Is it okay? And then in between, after this cavity and then it is coming back, that is a free falling thing. So it's a non-interacting zone. So that's how the Ramsey interferometry is 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 done in atomic fountain. And why it is fountain? Because it looks like fountain. You know, in water fountain, the water molecules goes up and then falls back. So it's just like, instead of water, it's a cesium atoms. That's why the name is fountain. And then they comes back and you detect them. So this is what exactly I described in my earlier slides, that you have two interaction zones while going through and coming back, and in between you have free evaluation. And then, okay, that's the entire picture, how it looks like. And a typical fountain, like actual experimental setup, this was a pictorial representation, but the actually something looks like that. You have an atomic oven and etc. The atoms are produced, it comes to this side, then there is a vacuum chamber where the lasers pass through all these viewports and etc. You create a cold sample of cesium atoms here, then you push them. This is the small one, is the microwave cavity, atoms goes through and comes back. And then this is another chamber on top of this where is the detection happens. This is how it looks like. And this is a real picture of the cesium fountain. This is from Swiss labs. Okay, and at this moment, the cesium fountain was invented in 90s. And at this moment, there are, I think, about 10 cesium fountain clocks which are operational in different parts of the world. In India, we had one cesium fountain. We built one cesium fountain, which was that is in NPL New Delhi, which was operational for some time until 2015. And since then, it is not operating, but they are trying to revive it again at this moment. So the best accuracy of the cesium clocks is something like 1.6 times 10 to the power minus 16 cesium fountain clocks, which use ultra cold sample of cesium atoms. So this again, you see, this is the fractional accuracy, and different cesium clocks, how they have improved their accuracies over the time. This is NPL India's fountain clock. In 2015, they reported some on the order of 10 to the power minus 15 fractional accuracy, and the best one is 1.6 times 10 to the power minus 16. So just one order of magnitude difference, but they are trying to revive these things again. Okay. Okay, so over last 100 years, so we have gone from free pendulum clock, we have reached to an optical clock. And now see that over some like last, let's say 40 years time period, how the UTC has improved. UTC is Universal Coordinated Time. If you remember that Fritz Rezel was telling about this definition. So this is UTC is a time scale which is maintained by atomic times, practically cesium clocks. Okay, so you see by implementing the laser cooled cesium clocks, there was a big jump, and then further systematics were improved, and at present the UTC is maintained with sub nanoseconds accuracy. That is the beauty, that how UTC was improved by incorporating better and better cesium clocks. And at this moment, even some of the optical clocks also contribute to the UTC, but not many. Okay, so these cesium clocks have reached to an accuracy of 10 to the power minus 16, which is very good for most of our present needs. For example, what are the needs? Like communication, navigation systems, GPS-based navigation systems. A very good clock is there. That's why your mobile phone works. That's why you get a good signal, a 5G signal on your mobile phone. You get a very good bandwidth for your internet. You get a very good HD quality picture on your television. All these things in the daily life we use, and all they use very good clocks. And 10 to the power minus 16 is mostly good enough for all these things. But that's not all, because we are improving our technologies. We are going from classical technologies to quantum technologies. For example, from classical communication, tomorrow we will use quantum communication. We will use a quantum computer, etc. There, this requirement of the clock accuracy will be even more stringent. Like today, a classical communication, like GPS communication, typically have an accuracy of few nanosecond to 10 nanosecond. But a quantum communication would require picosecond accuracy. How do you achieve that? Then this is not a good clock. So you have to build, you have to think, and you have to build a better clock systems. And that is like what optical clock, which I will not describe, but there will be 2 more lectures on that. So why optical clock is useful? Because the clock, you remember, if you remember the definition of Allen Davidson, again, I am not going, that is basically tells you stability of anything, Allen deviation. And that has two quantities, delta nu by nu zero, and the statistical accuracy. So by the way, what I wanted to say you basically, if you go from microwave to optical clock, this nu zero is manifold larger. For microwave clock, you have seen it is like 9.2 gigahertz for cesium, and for rubidium, it is 6.8 gigahertz. So let's say roughly speaking, 10 to the power 10 hertz. But for an optical transition, this nu zero is 10 to the power 15 hertz. So 5 orders of magnitude straight away higher. And since this nu zero comes into the denominator, your Allen deviation or the Q factor of the clock increases by several orders of magnitude by going from lower frequency to the other frequency. Or if you remember my first, without any analytical formula, my definition, like if you take an oscillator which is oscillating very fast, then if you miss one count, you have a better chance to make a more accurate clock. That's basically what it is. Okay, I'm skipping that. So cesium fountain clocks, I already told you that what are the best reached accuracies. And now there are two different type of optical clocks. One is based on neutral atoms, and they have, this one have reached to an accuracy, best one is 2 times 10 to the power minus 18. And the optical clock, which is based on the ions, they have reached to an accuracy of 10 to the power minus 18 again, but just slightly away, but let's say in the same order of magnitude, or basically in the same level. And they are like 2 orders of magnitude better compared to the cesium fountain clocks. Okay. So now I want to show you this slide. This is the history of atomic clock starting from Rabi. I told you how Rabi told us that use atoms, then you can make a better clock in 1945. Until let's say in 2026, because there is an expectation of redefinition of SI second based on optical clocks and etc. What are the major things has happened? I'm not going to read all of them, but some of them, like after Rabi, Ramsey was telling us about this betterment of the spectroscopy or better measurement of the better way of measuring this frequency with better accuracies. Then in 1955, cesium atomic clock was invented in NPL UK by SN and Perry. And within 3 years, that was commercialized. So this small box, what I was showing you, that was available in 1957, 58. Within 3 years, this small commercial box was available in the market by Hewlett Packard at this time, HP. Okay, then in 1967, the SI second was redefined with respect to atomic clock. Before that, it was based on the solar time scale, GMT, Greenwich Mean Time. In 1967, atomic clocks were all set, and there was a redefinition happened in 1967 based on atomic clock, and the second one we are expecting in 26, but I'm sure it will not happen in 26. It's pushed to another 4 years. 1993, cesium fountain clock was demonstrated by a lab in Paris, yet. And then afterwards, many other countries also developed that, including India. The optical clock first concept came in 2001. Yeah, and immediately it was practically realized by these ion trap groups, because in NIST, people who are doing ion trapping, there was a strong group on ion trapping, particularly for precision spectroscopy and etc. And they found out that we can immediately do it, and it was immediately realized in ion traps. And later on in 2005, it was realized in the optical lattice clock. So far, as I told you in my previous slide, that I trapped ion optical clock and neutral atom optical lattice clock, they have reached to similar level of accuracies. Okay. Now let's see that how many Nobel Prize in related techniques these are used in atomic clocks. Not exactly on that, but the techniques those are used in to develop atomic clock at different levels. How many people have got Nobel Prize? So it starts with Rabi, then Ramsey and Solow, then Hans Demmelt and Wolfgang Paul for ion trapping and all these things. Then Bill Phillips, Claude Cohen Tonuji, and Steve Chu, they got in laser cooling, which is used in fountain clock or trapped iron clock or lattice clocks. Then Dave Wineland recently, now before that, these three guys, Ted Hunch, John Hall, and Glauber, they got it for frequency comb, which I actually didn't touch upon, but I'm sure Tanya will touch upon. That is used for you making these optical clocks, and recently Demelt, Wineland. So these are the reason I'm showing you this slide. You can now have an understanding that what kind of sophistication of the technology has gone into this development of the optical clock, and then only you get sort of fractional accuracy 10 to the power minus 18. Okay, so 10 to the power minus 16 is good for many purposes, but not for all purposes. So optical clock is developed, and they have reached sort of 10 to the power minus 19 level. They will be very useful for many advanced purpose like quantum communications and etc. But then if I want to use this optical clock as a sensor, like let's say sensing gravitational waves or dark matter or something like that, I'm not going into detail, and even 10 to the power minus 19 is not enough. We need even a better clock. And that's why there are always a force to make a better clock, better and better clock. For example, after this optical atomic clock, people are trying for building a nuclear clock. You remember somebody asked to phrase, and he was saying thorium nucleus, and then measuring a clock transition in thorium nucleus, or highly charged ion clock, or clock based on molecules and etc., which is expected to give another 2 orders of magnitude betterment. That means 10 to the power minus 20, 21, and etc. And probably those clocks will be have a much better chance to do this kind of fundamental science and etc. So this field is practically has no ending. I showed you, the reason I showed you the 700 years picture, and you have seen how it has improved. Still, it has not reached to any end. It's just growing. We need better and better clock for many, many purposes. We have to put this kind of extremely accurate clocks in space and have to make a network of clock. Even you have seen the pulsar timing array, you probably know this thing that pulsar timing array is basically nothing but an array of clocks, but these are pulsar clocks, and they detected these gravitational waves. Instead, if we can have a real atomic clock, which has actually much better accuracy compared to pulsar clocks, then we can even increase this band of detection in the gravitational waves. You have probably seen one picture, one plot Rana was showing. There is one gap where the atomic clock network in space can detect that gap. Okay. Why optical atomic clocks? So that's what basically I just told you, but let me just go quickly. We have to keep in mind the redefinition of second. The redefinition can happen any day, in coming years. So that's why we have to build we have to have the capability of building these kind of clocks in the country, because these have many strategic applications. We cannot rely on buying these things from any other countries and etc. So for example, I want to give an example here that why it is important to indigenize this kind of technology. In our country, ISRO is a very successful institution which frequently put satellites into space, and we are expecting tomorrow Chandrayaan 3. Many of the satellites in ISRO, they failed because of their failure in the clock. Every satellite has multiple rubidium clock on board. And these rubidium clocks, so far, ISRO was buying from foreign countries, from Israel or from Switzerland. And many of the countries have actually export control of these clocks because they are strategic applications. So ISRO realized that thing, and because if you send a satellite and the clock fails, basically the entire mission is just gone. It's a waste of lot of money. So ISRO started indigenization of these rubidium clocks almost 15 years back, and recently they have completed it. And one of the rubidium clock, our Indian-made rubidium clock, is now in space. It just happened last month. So today the rubidium clock is serving purpose in the satellites, but tomorrow it will be optical clock in space, because the rubidium clock will not be good enough for the satellites. Okay, so we have to then build this kind of clock technology. First, we have to realize the technology in the lab in a big optics table, big lab, etc. Then we have to think how to make it compact and etc. Then after that, we have to think how to make it space qualified. And so it takes enormous time. It just doesn't happen overnight. Okay. Then I mean, these things I already told you, like with the advancement of the technologies like communication or navigations and etc., going to more quantum enhanced technologies, requirement of the accuracy of the clocks is becoming much more and more stringent. So we have to have this kind of better clocks. There are different kind of sensings, for example, geodetic measurements, measuring how the spinning or orientation of the earth is changing a little bit. It's not constant, it changes a little bit due to the volcanic eruptions and so on, so on. We can keep track of that using the clock network. Detection of the gravitational waves and so on, so on. We need a much better and better clock compared to what we have today. And finally, testing the standard model. You have learned a lot of lectures, BSM, Beyond Standard Model from Amar Bhuta. So those things can also be tested using the clock networks. And particularly for these two things, even 10 to the power minus 19 clock has gone to a limit. We need a better clock compared to 10 to the power minus 9. So there is always a force to make better clock. Okay, so far, is there any questions? Because last maybe 5 minutes, I'm going to speak a little bit about what we are doing in the lab, because until now it was just a normal lecture on microwave clocks and so on. So I just want to advertise in last 2-3 minutes that what we are doing. But until now, is there any questions? Yeah.
So, sir, when in 1968 this atomic clock is adopted, so how this number 9.192631770 gigahertz is taken as a reference to 1 second?
Yeah, so it was decided, the definition was decided based on cesium transition. And if you remember, the cesium splitting between two hyperfine ground state of cesium transition is this 9.19 to this transition. So that's a definition, because that's the transition frequency between cesium atoms. And why cesium? Why not rubidium? Because I told you some advantages of cesium, that it's like one isotope which is only available, which is non-radioactive. If you take rubidium, then rubidium has many, like let's say natural isotopes, rubidium 85, rubidium 87, and so on. So first you have to start with an isotope selectivity. Otherwise, for different isotopes, there is an isotope shift of the transition. If you want to make a reference, you have to make sure that which isotope you are using. But for cesium, it's just naturally available. You don't need to make any isotope selectivity or anything.
I have one question. So when this first redefinition of second was done, was there some extra time added or subtracted?
That is something different. What you are talking about, that is leap second. This extra time, like 1 second, sometimes we add or sometimes we subtract.
So we changed the definition, right? So historically there would be some lag or.
No. It's not like, it's not something like, let's say you buy a new laptop and you unscrew everything and you put your new laptop and screw up everything, all the connection. It's not like that. It goes parallelly. So no, we did not lose any time, I think, in our life. Maybe we lost something in COVID, but not otherwise. Okay, yeah.
You mentioned about the line width. I was wondering if we can improve the queue of the.
Sorry, can you repeat once more?
Yeah, you mentioned about the limitation of because of the line width of these transitions, of the forbidden transitions. I was wondering if we can actually like increase the queues of those microwave cavities very highly and then get a Purcell kind of enhancement and get a reduction in lifetime. For those transitions?
I do not understand what do you mean by Q of the cavity. Q of the cavity won't change this delta nu by nu zero, which is intrinsic property of the atom. Am I following you, or you want?
Yeah, but that would change the lifetime of the transition, right? Of the excited state.
No, lifetime of the excited state is property of the atoms. No one can change it. No, there is no. There is no coupling.
No, but can we do that, like by introducing a coupled resonator
Okay, so you basically mean by some hooks and crooks, if we can increase the lifetime of the excited state and make this transition much more narrower.
Yeah.
That's what you mean?
Yeah.
See, that won't work, because then practically there is no advantage of having an atom, because you cannot increase the lifetime of the excited state exactly same way in different instruments. You want to use intrinsic property of the atom, which is identical for all atom in every case. Yeah, so that won't work.
Okay.
Yeah.
So for the nuclear clocks, we know that nuclear transitions is much smaller than the optical transition. So why we are taking that nuclear clocks will be better?
But you know, like in general, your statement is absolutely correct, but there are some exceptions. So there is some nuclear transitions which fall into the optical domain. For example, this thorium-229 has a nuclear transition. The transition wavelength is not exactly determined yet, but theoretical calculation says it's something between 150 to, let's say, 170 nanometer, which is in the deep ultraviolet domain. And that's why the nuclear clock is being tried out with thorium nucleus. And they, if you heard the talk from Phrase, they are trying for last 10 years to look for this transition, which is extremely difficult thing. Yeah. You have one more question? Yeah.
Sir, what about its line with
the nuclear transition?
Transition.
This will have a very, very narrow line with. See, practically you have to keep it in mind. Say, for example, forget about nuclear transition. Let's say the ytterbium ion octopole transition, I told you the line width is 3 nanohertz. But you cannot reach to that line width. That 3 nanohertz line width is practically useless, because you cannot create a laser which has that narrow line width. The best laser has a line width of 8 millihertz, and that is only one available in the world. So typical, even 1 hertz line width laser is extremely difficult to create. It's an heroic effort. In our lab, we have created 140 millihertz. That's an heroic effort. That's like 2 PhD theses. Yeah. So you are practically not at this moment limited by line width of the transition, but limited by line width of the laser. But maybe I can tell you, ask your question in a slightly different way, that why the nuclear transition is useful if the line width doesn't matter. It's because the nuclear is very much shielded. Outside of the nucleus, there are electrons. So any perturbations, it's majorly affects to the electrons, not to the nucleus. So that means all these quadrupole shift, BBR shift, blah, 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 these are almost like zero, let's say practically, not practically, like very close to zero for nuclear transition. So it's a nearly unperturbed transition. So all these systematics, what you have to always derive and estimate and subtract or add something that you don't need to do in nuclear transitions. That's the advantage.
Hello. Yeah, so regarding the fractional inaccuracy compared to dipole transition and quadrupole transitions. So in quadrupole transitions, the lifetime is much higher, which means, let's say for a given second, there will be less number of excitations compared to the dipole transitions.
Right.
So this enhancement of the number of excitations in dipole is actually very high compared to quadrupole. So is this count being taken to evaluate the fractional inaccuracy, where delta nu by nu?
Yeah.
So
what you are saying is slightly different. See, delta nu by nu is like depends on nu and delta nu. But what probably you are saying, trying to say, if I understand correctly, that the atom will be excited to the excitation, it will stay there forever. So you won't get any signal photon, right?
No.
Okay.
For a given time,
yeah,
I have, let's say 10 power 6 transitions in dipole. But in that same amount of time, I might have only 100 transitions in a quadrupole.
Right.
So this 10 power 6 is basically a statistical enhancement in the dipole, right?
Okay, I understand. No, but in this case, it's not like pendulum and you are watching that how many oscillations it is happening. No, it's not like that. You are exciting the transition, and once the atom or ion is excited to the excited state, it might be just one. You don't need to even have 10 or 100, it's just 1, then you know that this excitation has happened. Okay, so the statistical thing for how many times it is rotating, that doesn't play a role here. And also what I was trying to say, the detection happens in a different way. It's not directly looking into the fluorescence of that particular transition, because you will get a photon once in a while. That will not go to your counter. So detection happens through a separate transition. Maybe we can discuss that part later. Yeah.
So you gave an example, an application of these clocks in putting them in space and searching for gravitational waves.
Okay.
So just like pulsar timing arrays, they are sensitive in nanohertz region, I think. So
I don't know the answer.
Oh,
I don't know the answer, because it's so your question is like, will there
which
be
range they are in? Like which range
so
atomic
it's
clocks?
actually in different frequency band. If you see that the gravitational waves, you are talking about gravitational waves, right? In the gravitational waves can happen in different frequencies, from nanohertz to hundreds of kilohertz. So the present LIGO is something like tens of hertz to some 2 kilohertz, etc. And then pulsar timing array, if I remember, this is some below 1 hertz and etc. But there is a certain gap where there is no detector, and that this clock network can do. And why the pulsars are also clock, right? So why they cannot do it? Because pulsars can slow down. Pulsars, the frequency is not really extremely precise. But atomic clock frequencies can be very, very precise. They won't slow down. Pulsars have a slowing down thing. Their spinning rates are not exactly constant. It's very much constant, but not exactly constant.
But can they work in LIGO's range also? Or?
No. It's not in
No.
the LIGO's range, not in the pulsar timing arrays range, but somewhere there is a gap in between.
Okay. Thank you.
Yeah. Any other questions? Yeah.
Subhadeep, my question is also related to him, that it's regarding more accurate clocks like nuclear clocks or molecular clocks. It is still the research that has to be done, or it is the technological advancement that is stopping?
No. The research has to be done there as well. For example, for the nuclear clock, everything has to be in the, like, first of all, how do you produce that nucleus? Yeah, that itself is a research. They have done that thing already. Yeah, but then second stage is finding out that transition. There is some theoretical calculations, but they yet could not find that transition. That's a part of research, spectroscopy. You have to find that transition. Then once you find that transitions, you have to do further things like putting your frequency comb, etc., all these things at that 155 nanometer wavelength, which is a very strange wavelength, right? So there are, of course, a lot of research to put that technology forward, obviously.
Means are we at some point of standard number at 10 to the power minus 18, that with this technology we cannot go further down?
That is limited by Heisenberg uncertainty principle. You can go as long as you don't hit the Heisenberg uncertainty principle.
But at this moment,
no,
I mean,
because
nuclear clocks is the only answer, and optical clock, is this the limit?
No. Optical clock is definitely not the limit. Even with the optical clock, the present technology, now everything is, the entire environment is at room temperature. People are trying to put the entire optical clock in a cryogenic environment. Then your black body radiation shift will be practically zero. So that is one of the major systematics which affects the clock transition, black body radiation. If you make the entire clock in a cryogenic chamber, your black body radiation becomes nearly zero. And then that accuracy will probably also go down by 1 order of magnitude. NIST USA, Kasturi's group, they are trying that thing. But still 1 order of magnitude is not that great. So nuclear clock or highly charged ion clocks probably will put it down 2, or something like expected is 2 orders of magnitude below.
I never heard of highly charged ion clock.
Oh yeah, so like argon 13 plus. Yeah, so that is like you are not in the valence electron anymore. You are in the much closer to the nuclear cells. Though the same thing, like your perturbations are much less, and that is easy to produce compared to nucleus.
But you also need to have the lasers at that.
Highly
level.
charged ion clocks recently have already been realized. Any others? Otherwise, just last few seconds for what we are doing in the lab. So, okay, so at IUCAA, I have settled a lab which is called Precision and Quantum Measurement Lab, and I started in like 2020. So our main goals are like Quantum metrology using ultra stable laser lights, precision measurements, hunting for new signs, practically like backbone is the optical atomic clock. So using the optical atomic clock, we want to do this kind of fundamental science, and developing quantum technologies related to that. Okay, so if I just put like what is required to build an optical atomic clock, then I can divide it into 5 segments. The first one is generation of the ultra stable sub-hertz line width laser, and this is the picture from our lab. So we have designed the cavity, and cavity is under fabrication at this moment. That requires quite heroic effort to get down to sub-hertz line width. Then second thing is like the vacuum chamber, ion trap, and all these kind of systems, so that you can trap a single ion and then you do laser cooling and etc. etc. Then you excite the clock transition. This is a solid work design, but we have all the components except the ion traps. And those guys know that we are like building the ion traps together with Sadiq Rangwala at RRI. They also need it for some different experiment. And it's not a normal ion trap, it's a very precision ion trap. That's why it's not that easy to machine these things. So we have, otherwise we have all the other components. Then if you drive the transition, you have to synthesize what is the frequency of this transition. That is optical frequency synthesization. And for that, you need to have a optical frequency comb. That's a commercial thing, but only buying optical frequency comb is not helpful. Just like buying a laser, you have to do many other things to make this optical frequency comb useful for optical frequency synthesization. And we already have optical frequency comb in the lab, and you see a known face here. Oops. Oh, okay. Fourth thing is like fiber phase noise cancellations. Like we want to transport a light even within the lab by few meters. The length of the fiber, if we transport it through the fiber length changes because of the temperature and stress and all these kind of things. And that is not acceptable. So you have to stabilize the length of the fiber, even if it is just 5 meter long fiber. So that technology we have already developed in the lab, and we can stabilize 100 kilometer long fiber with 10 to the power minus 18 level of stability and etc. And the fifth thing is controlling this entire thing using the computer control. You don't want anybody to go and turn some knobs, etc. You just practically want to sit at home, and from your iPad, you want to just click a button and everything should work. That's practically like no human intervention. So that's also quite a difficult thing to develop, and we are working on that part as well. So all the pictures what you see is from our lab. Now, these developments are not necessarily only useful for clock, but they have many other applications. For example, like this trapped ion, this is a platform for quantum computer as well. This is a platform for quantum simulator, precision spectroscopy, sensing, quantum engine, and anything. Not that I am going to do everything. No, I am not going to do everything. But this technology, once it is developed in the country, somebody else can do it. For example, myself and Sadiq are developing the ion trap together, but both of us have different purpose. So once we standardize this ion trap technology, maybe some other person who wants to do quantum simulator using trapped ion, he can also use it, or she can also use it. Similarly, narrow line width laser, like precision spectroscopy uses that, optical qubits require that, like LIGO and all these things, they use it. So there are multiple applications. Similarly, all others, I am not reading all these things, but if you want to know, we can discuss it later. I also see there is not too much time. So yes, so that's basically my last slide. So thank you.